Hello students. So in our last video lecture we have studied about the buckling curve, and we have also studied about the concept behind this construction of buckling curve, and I have already mentioned that there are four different buckling curve which is possible, and this possibility depends on the property of cross sections. So in today's video lecture we will get this idea about these different properties of the cross sections, and also we will study about the different guidelines or parameters which will be useful for the numerical problems. Okay, so in last lecture I have explained about the local buckling failure, and as I have explained, this local buckling failure depends on the property of the cross section. So this property is basically limiting width by thickness ratio. So depending on this limiting width by thickness, the failure behavior will be different for different class of sections. Okay, now we can get this idea from table 2 of Indian Standard Code 800. Okay, IS 800. So let us go to table 2. So you can see this in this table 2 some limiting width to thickness ratio is mentioned, and on the heading it is compression element, it is ratio, it is class of sections, class 1, class 2, class 3, and there are one more class 4. So class 4 is not in your uh, syllabus, or not is not designed. Okay, so these what are these class of sections? So we can get this idea about this class on clause number 3.7. so it will be mentioned here. Okay, different classes, and for different classes the failure behavior or the stress, uh, I mean when you apply some load, okay, how it will be stress, and when what will be the failure behavior, that is uh, that is what this class. Okay, so depending on the failure behavior these classes are categorized, and this class depends on the ratio. Okay, here it is mentioned. So b by tf, b by tf, okay, like this, b or breadth by thickness or depth by thickness. Okay, so suppose you are dealing with one particular cross section, so you have to see in which category it will come. So from this column you have to just select that particular row in which category this compression element will come. Then after that, suppose your compression member is coming within this category, so you have to see this b by tf, and you have to verify in which category it is coming. That means you have to find the value of b by tf, and check the value of 8.4 epsilon, 9.4 epsilon, 13.6 epsilon. So if the b by tf is coming within this 8.4 epsilon, then it will be plastic section or class 1 section, or if it is coming above this 8.4 epsilon and less than this 9.4 epsilon, so it will be class 2 sections or compact sections, and so on. Okay, now what is this epsilon? So epsilon is mentioned here in notes, so you should read these notes, all of 5 notes. And epsilon is equal to root under 250 by fy. Okay, so this 3 point is important, we will explain it later, you can read it. Now after that, let us go to table uh, page number 20. So in this maximum effective slenderness ratios is mentioned here. So as I already explained, this strength of column depends on the effective slenderness ratio. So if the ratio it becomes more, that means your column becomes more slender. That means there is a maximum chances of buckling. So there should be a maximum limit, okay, up to which we can use a member as a commission member. Okay, now what is the limit? So limits are mentioned here in table number 3. Okay, so as we are designing, we will be dealing with the compression member, so you have to read this point 1. So for point 1 It is mentioned that a member carrying compressive loads resulting from dead load and imposed load, it should be 180. So whatever you will design, you will select your compression member. So the maximum ratio should be 180. Okay, not more than 180. Okay, then let us go to figure 8. So this figure 8 you will get it from section 7, design of compression member. So every guidelines for designing compression member will be available in this section 7. Okay, so in section 7 we have got this buckling curve, one buckling curve. So I have explained there are four buckling curve possible, and this buckling A B C D, that means four buckling curve. So this A B C D, A buckling class, B buckling class. So this depends on the property of cross section. So it is mentioned here, you can see in clause number 7.1.2.2. So the classification of different sections under different buckling class A, B, C, D is given in table number 10. So let us go to table number 10. So you can see in table number 10, it is all about buckling class of cross sections. So there are different cross sections, that means four cross sections, and for uh, every cross sections the buckling class depends on the this limits. Okay, so suppose your cross section is a rolled steel I sections, so it will have two axes, this axis y axis and this is z axis. Okay, so it this on I mean this column can buckle about this y axis or it can buckle about this z axis. So in which axis which buckling class curve should be selected? Okay, so that depends on these limits. Okay, suppose this is a rolled slice section, so you have to find this h by bf. If it is more than 1.2 and tf is becoming less than equal to 40 millimeters, so for that criteria, okay, you should select this buckling class, that means this one. So suppose you want to find the design strength about this zz axis. Okay, suppose this column, okay, there is a chances to buckle about this zz axis. Then which buckling curve should be selected? So that is buckling curve A. Okay, suppose this column may buckle about this y axis. So in case you want to find the design strength about this y axis, so you have to go for this class buckling class B. Okay, so you have to suitably select this buckling class for finding the design strength of a cross sections. Okay, now you can get this buckling class idea from this table 10. So there are different cross sections available: C sections, angle section, T section, and these are different sections. So for different sections, so the buckling class will be different. So it will be you will get it from this table 10. Okay, now go to this figure 8. So these are the ABCD buckling class. Okay, now let us understand the design parameters or design guidelines for compression member. So for a compression member, design load carrying capacity or load carrying capacity, that is equal to PD. Okay, PD is equal to how much? PD is equal to area into stress, area of cross section, and stress carrying capacity. Okay, now area, suppose you are using a I section, okay, as a compression member, then you can find the area of the cross sections. Okay, and if you can find this FCD, then you can understand, you can know the load carrying capacity of that particular sections. Okay, so our task will be to find this FCD, because this area of that particular element or cross section will be provided by the steel table. So in steel table there are different cross sections Okay, that will be mentioned, and you have to find your cross sections on that steel table, and you have to find the area. So you will directly get it from the steel table. Now you have to find this FCD. Okay, now FCD can be found from this equation. So FCD is written here. FCD is equal to this equation. Okay, equal to this equation. Okay, so this is nothing but the stress reduction factor is mentioned here. You can see this is stress reduction factor. Okay, so to find this FCD, you can use this equation, or you can use this equation, or you can use graphical method. Okay, so now let us understand about these equations. Suppose this is the first equation. Okay, Fy by root under gamma m0 by phi plus within third bracket phi square minus lambda square to the power half. So phi is equal to this. So in this equation, phi is dependent on this alpha and this lambda. Okay, so what is this lambda? Lambda I already mentioned. This is non-dimensional slenderness ratio, that is Fy root under Fy by FCC. Okay, that means along this axis, that is non-dimensional slenderness ratio. Okay, so it is Fy by FCC to the power half. So you can get it right from the equation, and then FCC is nothing but the Euler buckling stress. So you will get it from this equation, and you know what is KL by R. So it is nothing but the effective slenderness ratio, and alpha is imperfection factor. It is given in table number 7, and this stress reduction factor in table number 8. Okay, so in this equation, this denominator is nothing but the this stress reduction factor. Okay, so you can find this stress reduction factor from this equation, or you can use table 8 to find this stress reduction factor. Okay, now for a particular cross section, okay, that means suppose we are having a I section. Okay, so for I section there are two axes, Z axis, this is Y axis. So you will get two different strength about this Y axis, about this Z axis. Okay, that means you have to find these two strength, and out of these two strength, the lesser one will be the governing strength for these cross sections. So what you have to do, you have to find this FCD for Y axis, then you have to find this FCD for Z axis. Okay, so when you are finding this FCD for Y axis, you should denote it by providing a suffix of y, phi y, lambda y, like this. Okay, so it will be phi y, here it will be alpha and lambda y, this. Okay, and this lambda y will be given from this equation. It is dependent on the this KL by R and this Fy. So here you have to find this K from this equation. So K depends on the support conditions or end restraints, as I have already explained in my previous video lectures. Okay, so I think it is very clear, and if there is any doubt, it will be cleared in the numerical sections. Okay, so now we can find this FCD for the two directions by these equations or by this part. So this stress reduction factor can be found from this equation or by the table. Okay, and third process is that this FCD can be found from the uh, table. So you can find this FCD from the table. First, this is the first method. Second one will be the using this part only, and third will be this FCD equal to this. Okay, and uh, you can find this part either by table 18 or by these equations. Okay, so in next lecture we'll go to the we'll go to the detailed discussion about the procedures uh, to design the compression member. Okay, and we'll select numerical.
So I forgot to mention one more thing. So in my previous video lecture we have got this buckling curve, and now in this video lecture we are using these different equations. So I want to say you that both are same thing, means the graphs are drawn from these equations only. So the equations they have followed here in the IS code. So you can use this equation what I have described, explain, or you can use this curve also, buckling curve also. For different buckling class you can find the non-dimensional slenderness ratio, and for that particular slenderness ratio you can go to the like this on a curve. Okay, so you can draw a vertical line and it will intersect that curve, particular curve, on a point, and you can get the FCD by Fy. So from that you can find the FCD. So that is also you can do. Okay, and you can use also the equations which I have explained. Okay, so don't be confused that we have understood everything based on the graphs, and now we are using these equations.